All right, let's talk about one of the biggest challenges you'll ever face in system design. What happens when that reliable, single database you built everything on just can't keep up anymore? We're going to dive into something called SQL sharding, and we're going to see why the idea of a single, perfect database is often just a really, really useful illusion. When we start building something new, we all live in this perfect world. And right at the center of that world is our single relational database. It's clean, it's simple, it works. And why do we love it so much? Well, it's because of the guarantees it gives us. A relational database makes sure our data is consistent, which, believe me, makes a developer's life a whole lot easier. It's our one source of truth, the foundation for our entire application. But then, you succeed. Your app takes off. You go from a few thousand users to millions. And that beautiful, simple database, it starts to buckle under the pressure. The illusion of that perfect world starts to shatter. So what's actually going on here? Why is our trusty database suddenly failing us? Well, it turns out there are a few fundamental bottlenecks baked right into its design. Let's pull back the curtain and look at them one by one. First up is the single lock manager. To keep data consistent, the database has to lock things when they're being changed. But when you have millions of requests flying in, that manager becomes like a single traffic cop at a massive intersection during rush hour. Everything gets serialized, a huge line forms, and the whole system just grinds to a halt. The next problem is something called the write-ahead log, or WAL. This thing is absolutely critical for durability. Every single change gets written here first. But it's a single log. We're talking about one file on one disk. There's a physical limit to how fast you can write to it, and that puts a hard ceiling on your database's performance. And finally, we have the buffer pool. Think of this as the database's short-term memory. It's RAM cache. When you're small, all the data people access frequently, the hot data, fits right in there. But as you grow, it doesn't fit anymore. So the database is constantly having to go back to the super slow disk to fetch data, and your performance just falls off a cliff. So you hit these physical limits, and you have this realization. You can't just keep buying a bigger, faster server. That's not a long-term solution. You have to fundamentally change the architecture. And that brings us to sharding. It's not some magic trick. It's a hard truth you have to face when you scale. So what exactly is sharding? Well, this picture says it all. You take that one giant, overloaded database and you split it up horizontally. You partition it into smaller, completely independent databases that we call shards. Each one holds its own piece of the puzzle. But how does your application know which piece of the puzzle to talk to? This is the clever part. You introduce a shard router and, crucially, a shard key. For most apps, this is going to be something like the user ID. So when a query for user 55 comes in, the router knows exactly which shard to send it to. The goal here is simple but powerful. Keep every query local to just one shard and keep everything fast. Now, choosing that shard key, it's probably the single most important decision you'll make in this whole process. You need three things from it. 1, high cardinality, lots of different values, so data spreads out evenly. 2, uniform access. You have to avoid one shard getting all the traffic, a hot shard, which can cause a meltdown. And 3, query locality, making sure almost every query can be answered by a single shard. If you mess up even one of these, you're not just looking at a slow system, you're looking at catastrophic failure. So great, we solved our scaling problem, right? Well, yes and no. We've actually just traded our old problem for a whole new set of challenges. By breaking up our database, we've stepped into the complex world of distributed systems. And out here, the old rules just don't apply. Remember all those amazing ACID guarantees we just took for granted? Atomic, consistent, isolated, durable? Yeah, in a sharded world, they kind of break. How can you guarantee a transaction that touches 2 different shards is all or nothing? How do you get a globally consistent order of events? You can, but it requires coordination between the shards. And coordination is the enemy of speed and scale. The classic textbook solution for this is something called a 2-phase commit. It's a protocol to make sure transactions happen atomically across different machines. First, a central coordinator asks all the shards involved, "Hey, are you ready to commit?" If they all vote yes, then the coordinator sends the final command, "Okay, do it." But here's the catch, and this is such a critical concept in system design. You're looking at a fundamental trade-off. 2-phase commit is great because it preserves the correctness of your data. Awesome. But, and this is a huge but, it sacrifices availability. Because what happens if that coordinator crashes in the middle of a transaction? Well, the shards involved can get stuck, holding locks, and basically freezing parts of your system until an engineer manually intervenes. All of this complexity is exactly why tools like Vitis exist. Vitis is this really smart middleware that sits between your application and all your database shards. It handles routing, helps with complex operations, all that good stuff. But it's not magic. Vitis doesn't erase the laws of distributed systems. It just gives you a powerful toolset to manage them. And that brings us to a classic mistake, a trap that even very senior engineers can fall into when they forget the first principles we've just talked about. This is what happens when the pure theory of sharding slams into the messy reality of new product features. Just look at this diagram. Your whole system is beautifully optimized for single-user actions. A query comes in, it hits one shard, and you get a response back in under 20 milliseconds. Perfect. But then some new feature, like an admin dashboard, needs to pull data from every user. Suddenly, one request has to fan out and hit every single shard at once. Your latency doesn't just go up, it explodes. Here's exactly how the trap gets sprung. You did everything right, you sharded by user ID, but then the product team comes along and says, we need an admin dashboard to see what all our users are doing. So you build it. And now, every time an admin loads that page, a query goes out to every single shard. Your P99 latency goes through the roof, and the poor on-call engineer gets an alert, looks at the monitoring, and sees the most confusing thing possible. Every individual database is perfectly healthy, but the app is unbearably slow. This isn't a bug in the code. It's not a hardware problem. This is a theory failure. The entire system was built on one sacred assumption: query locality, and you just introduced a feature that completely violates it. The architecture is doing exactly what it was designed to do, and it's punishing you for breaking the rules. So if we really want to build systems that can scale, we need more than just a quick fix. We need to actually change the way we think. We need to adopt a totally new mental model and just embrace the fact that we're living in a distributed world now. And if there's one thing you take away from this, let it be this quote. Read it again. Sharding is not scaling a database. It is scaling by giving up the idea of one. You're not making your database bigger. You're acknowledging that bigger has a limit, and you're moving to a fundamentally different, distributed architecture instead. And that really brings us to the final question, one for you to think about. This idea of a single system illusion, it doesn't just apply to databases. So take a hard look at your own architecture. What convenient illusion are you relying on right now? And what happens when it finally breaks?